Hey Ramblers, this video covers chapter 7.1 in our textbook and deals with the topic of integration by substitution. Now up to this point, all of the antiderivatives we found came from integrals that were themselves pretty basic antiderivatives. Or I should say, they were basic derivatives of basic antiderivatives. So learning this new technique called substitution is going to allow us to start dealing with some more complicated functions than just the basic ones. Now, you may remember back to first semester, we learned the chain rule. Now, the chain rule was for functions that were in another function. When we were taking the derivative, we took the derivative of the outside function and the derivative of the inside function. You may remember that. Well, substitution is going to be the means of integrating functions that are the derivative as a result of the chain rule. So in other words, we are undoing the chain rule with substitution. It's kind of complicated at first, but once you practice it a little bit, and we'll get lots of practice in class, you'll begin to pick up the technique. Ramblers, please pause often, take notes. We're going to be showing you a lot of examples here. So pause the video, work through the examples, and I hope this helps. Thanks for watching. Since the substitution method of integration is undoing the chain rule, maybe it would make a little sense to review what the chain rule said. The chain rule is used whenever we are when we're differentiating a composite function. That's where we have a function like g of x inside another function like f of x. Let's look at an example of that. The sine of x cubed is a composite function. The x cubed function is clearly inside of the sine function. So when we take the derivative, as you recall, the chain rule tells us to take the derivative of the outside without changing the inside. So g of x, at least at first, remains unchanged. And then we multiply by the derivative of the inside. So that looks like, in our example, we take the derivative of sine, which of course is cosine, and we're not going to change the inside function, x cubed. But then we'll multiply by the derivative of the inside function, which is of course 3x squared. So when we are integrating and moving backwards, notice that we would be starting with the derivative. That is to say, this answer here is what we're going to be integrating. So we're going to want to find integrals that have a function inside of another function and the derivative of that function. So an example of that, of course, would be the integral of 3x squared sine x cubed. And once again, you can see a function inside of another function, so x cubed is inside of sine, and the derivative of that inside function is outside. So that gives you, there's your f of x, there's your g of x, and here's your g prime of x. Okay, let's take a look at how we're going to formally do this in the next slide. Okay, let's get this in your notes. Just to remind us of what we're trying to undo, here is the form of integrals that will work with substitution. Again, it's going to be a composite function where the inside function's derivative is also present. So let's take a look at this first example here. We see x cubed inside the cosine function, and there is the derivative of x cubed, or the derivative of the inside function, 3x squared. So just so we're kind of talking the same language, I want you to start letting w be the inside function, and w prime will equal dw dx. So we can rewrite our function this way? Well, let's just start it at 3x squared times the cosine of x cubed, like we had originally. But then underneath, I say w equals the inside function x cubed, and w is always going to equal the inside function. Then dw dx, which is w's derivative, equals 3x squared. Now the way this works is that we only want to have w's over on the left side of the equal sign and all the x's over on the right side. So I'm going to take the dx that was in the denominator and multiply both sides by dx. That's going to cancel out over on the left side. So I have all my x's on the right side, all my w's on the other. Now I'm going to rewrite my integral, but you'll notice that the 3x squared is now part of what's represented as dw. So I can rewrite it as cosine of w dw, because inside that dw is my 3x squared dx, and inside the w, or represented by the w, is x cubed. So now looking at this should be a function that you know how to integrate. We know that the integral, or the antiderivative of cosine, is just sine of w plus c. Now when we're finished integrating, as we just are, we substitute back. So your final answer would be sine of, instead of w, we write x cubed plus c, and that's your final answer. Okay, let's try another couple of examples until you get the hang of this. Okay, so take a look at this function here, and let's try and integrate it. I can see that it is a candidate for substitution because there is a function x squared that's inside the e function, and the derivative of that inside function is there, 2x. So let's try using substitution. W is going to equal my inside function, x squared, and rather than solve for the dw, I'm just going to start out writing that dw is going to equal 2x dx, and skip that step of having to multiply both sides by dx. Alright, now that I have all w's on the left side and x's on the right, I'm just going to rewrite my integral with w's. So 2x is part of my dw, so I'm really just left with e to the w dw, because again, the dw represents the 2x and the dx, and w represents the x squared. So I know how to integrate that. That's just going to be e to the w plus c. Now that I've integrated that, I can substitute back, and so that equals e to the x squared plus c, which is, of course, my final answer. Alright, let's try another one. Okay, well, here we have the integral of 3x squared times x cubed plus 4 squared. So I want you to pause the video and try integrating this yourself. Remember, what you're going to want to find is an inside function, and we'll set that equal to w, and the derivative of the inside function, and we'll set that equal to dw. Now pause the video and try to do this by substitution. Okay, your inside function is definitely x cubed plus 4. The derivative of that is going to be 3x squared dx. So I can rewrite my integral as the integral of w squared, my 3x squared and my dx are part of the dw, so my full integral becomes w squared dw. Okay, to integrate this, that's just going to be undoing the power rule, so I get w cubed over 3 plus c. Now resubstituting, I get x cubed plus 4 cubed over 3 plus c. Okay, let's take a look at one more example like this, and then I want to throw one other change or a wrinkle that can come up with these kind of problems. Okay, consider this one. Sine x to the 6th times cosine x. Now remember, another way of writing sine x to the 6th is just put sine in parentheses raised to the 6th power. Now pause the video, see if you can figure out which function is an inside function and set that equal to w, and then its derivative should be there, and that would be dw. Okay, pause the video and give it a shot. All right, hopefully you recognized that my inside function is going to be the sine of x, and we know that the derivative of the sine of x is cosine x dx. So I can rewrite all of this as w to the 6th power dw, because the dw represents my cosine x and the dx, and now I can integrate. Well, now I just undo the power rule, so this becomes w to the 7th over 7 plus c, and when I substitute back in that for w, I get sine of x to the 7th over 7 plus c. All right, Ramblers, let's take a look at a couple examples at what happens when we're off by a constant. Okay, sometimes we use substitution even though we don't see exactly a function inside another function and its derivative in the integral. So let's take, for example, this one. Clearly 3x is inside the e function, and the derivative of 3x would be 3, but there isn't any 3 inside my integral. So how do I handle that? Well, if this is a very important point. Substitution works if the integrand, that's the thing we're trying to take the integral of, contains the derivative of the inside function to within a constant factor. Let me show you what I mean. So let's rewrite this, e to the 3x dx. W is always my inside function, so that's 3x, and the derivative dw is just going to equal 3 dx. Now, as I look at my original integrand, there is no extra 3 hanging around. So what I have to do is divide both sides by 3 so that the 3's cancel on the right side, and I have a 1/3 as a constant on the left side. So I take that 1/3 and rewrite or substitute into my integrand, and I got e to the w dw times 1/3. So we know that that 1/3 just stays along as we integrate, and so integrating e to the w gives me e to the w plus c. Now I resubstitute, and I get 1/3 e to the 3x plus c, which of course is the antiderivative. Let's try another one where we're going to use substitution even though our integrand does not contain the derivative. It's off by a constant. Okay, in this example, I have a function inside another function, clearly, and x to the 3rd would be the derivative of x to the 4th plus 5, but it's a little bit off, isn't it? The derivative of x to the 4th plus 5 would be 4x cubed, not just plain x cubed. But let's see if we can do this anyway. So my w is going to be the inside function, x to the 4th plus 5, and then my derivative dw is going to equal 4x cubed. Since there is no 4 I will divide both sides by 4. They cancel out on the right side, and I'm left with dw over 4 equals x cubed dx. Sorry, I should have been writing that dx all along. So I can now rewrite my integral with a 1/4 in the front, and now I've got the integral of the square root of w dw. Of course, I have an easier time integrating that if that's w to the 1/2. And so I can integrate 1/4 w to the 3/2 divided by 3/2 plus c, which is going to be 1/4 times 2/3 w to the 3/2 plus c, which is 1/6 w to the 3/2. So our final answer after we substitute back in is x to the 4th plus 5 raised to the 3/2 power over 6 plus c. Okay, Ramblers, let me give you one more chance to integrate, even though we're off by a constant, and then we're going to look at one other important technique to know. Ramblers, why don't you try this one? Pause the video and see if you can't use substitution to integrate this. Pause the video and give it a shot. Okay, hopefully we recognize that the inside function is x squared. That's definitely inside the cosine function. And so the derivative is going to be 2x dx. But of course there is no there is no 2 in our integrand. So we're going to have to divide both sides by 2. And we get dw over 2 equals x dx. So that means I've got everything accounted for. My x, my dx, and my x squared. So I can rewrite this function as the integral of cosine of w dw. And my constant in front is 1/2. So when I integrate that, I get 1/2 sine of w plus c, which is 1/2 sine of x squared plus c. If you take the derivative of that, you're going to see that you get exactly what we just integrated. Okay, there's one last example I want to show you, and really it's a technique you'll be using in the exercises just to be aware of. Sometimes we don't recognize a function as being in another function. So here's a trick to look for. Sometimes being in the denominator is an inside function. So here I'm going to let w equal 1 plus e to the t, and the derivative of that, of course, is just e to the t dt. I left that off here. So let's try rewriting that. I have the integral of 1 over w, and now my dt is taken care of in the dw, my et is taken care of in the dw, and w takes care of the denominator. So as I rewrite this, everything is taken care of. And I see that I have the natural log, when I integrate that, I get the natural log of w plus c, which when I resubstitute is just the natural log of 1 plus e to the t plus c. Now, to get fancy, I know that 1 plus e to the t is always positive. E is always positive, and so is 1. So I can just rewrite this as the natural log of 1 plus e to the t plus c, and just get rid of the absolute value signs. Okay, there's your final answer. We'll have lots of practice with this technique, Ramblers. Thanks for watching.